Hi, everyone. Welcome back. This is part 3. We're going to be talking about the neuroscience of aphasia, what we know right now. We're constantly learning new things. Neuroscience is a rapidly changing field. I'm going to focus on cognitive neuroscience, which means understanding how we look at language from a more global perspective of the brain, so not cellular, more high-level neuroscience. So we call that cognitive neuroscience in the field. So that's what we'll be talking about today. Historically, we think about two areas of the brain being important for language. Now, this idea goes back to the 1860s. Pictured on the right is Carl Wernicke at the top, Paul Broca at the bottom. Now, they're not the only people who were active in thinking about aphasia and how it relates to the brain at this time, but they're definitely the most famous. Wernicke identified a patient, which you can see a slice, well, technically the outside of their brain there at the top, who had some individual differences in understanding and speaking. And so what Wernicke noticed was that this person tended to not really understand what was being said to him. And when he produced language that was pretty much meaningless. It didn't carry much content. You may have heard this termed as word salad, producing a bunch of words that really don't make sense. So Wernicke, when that patient died, dissected his brain and found what you see there at the top, which was extensive damage to what we now call the posterior temporal cortex in the left hemisphere and extending into the inferior parietal cortex. Paul Broca, on the other hand, had a patient who looked a little bit different from Wernicke's patient. This was patient Tan. This individual had extreme difficulty producing language. He really only said a few words. That's why he's called patient Tan, because Tan was one of the few words he said. And he didn't seem to have any issues with understanding speech, unlike Wernicke's patient. And so Broca, when this individual died, also dissected his brain. You can see it at the bottom left there. And this brain had a very different damage profile than Wernicke's brain. I should say Wernicke's patient's brain. This damage profile was also in the left hemisphere, but it was more confined to the frontal lobe, in particular the inferior frontal gyrus. Now today, people still term these two unique brain profiles as being Broca's area, which is left hemisphere, inferior frontal gyrus. In particular, there are 3 sections of that gyrus. Broca's area is technically the posterior 2 sections, meaning the sections that are more toward the back of the brain. And then for Wernicke, there's an area called Wernicke's area, but this is really not structurally an area. It's a location in the brain that's posterior superior temporal gyrus and inferior parietal cortex. So it's not really a localized gyrus like Broca's area is. If you're interested in the history of aphasia, in particular brain and behavior relationships, I've listed a great article here, and there's also a podcast that details a lot of the history of aphasia and how we understand the neurobiology of language. Because of Broca and Wernicke's findings on the prior slide, many people had a modular idea of language, meaning that one area in the brain was particularly specialized, or even the only area in the brain that could do specific language functions. So a really common interpretation of Broca's finding was that damage to Broca's area impaired speech production, and that was a well-held view for many years. What I'm showing you on this slide is where we are right now in terms of thinking about how language is represented in the brain. It's a little bit less modular, meaning that we typically acknowledge in the field that certain brain areas are specialized for doing certain things, but that typically it's the interaction between brain areas that creates our ability to do things like language. So on the left, you can see the dual stream of language model. This was a paper that came out in 2004, and then there have been several iterations, 2007 and such, from these two authors, Hickok and Popel, who discussed one way of thinking about how the brain is organized to work together to do all of our language functions. So what you can see is in the bottom section, there are two brains. There's a left hemisphere sagittal slice and a right hemisphere sagittal slice, and they're color-coded. The color codes line up with the schematic on top, and I've outlined the acronyms below just in case you're not as familiar with brain terminology. Broadly, we think of the dual stream model as containing a ventral stream and a dorsal stream. Chang's group on the right created a nice schematic for a neurosurgery journal, highlighting broadly the same thing, just simplifying it a little bit for viewing purposes. The dorsal stream in Chang's diagram on the right is in red, and the ventral stream is in that purple color. Notice he's not showing a right hemisphere, but the right hemisphere section would show mostly the purple color. So what we've learned is that the ventral stream we think is bilateral, meaning it uses left and right hemisphere areas, and the dorsal stream we think is largely in the dominant hemisphere. Now, I don't say left hemisphere because we don't think that everyone's left hemisphere is dominant for language, but we do think the majority of people, the left hemisphere is dominant for language. So for most purposes, we can say left hemisphere is where the dorsal stream largely is. Now, the dorsal stream can be thought of as the stream that helps translate sounds into speech. It's the production stream. So when we want to say something out loud, like what I'm doing right now, we of course have to find the sounds of those words and then send that to our speech interface. And so that's what we think the dorsal stream does. The ventral stream, on the other hand, we think is very useful for interpreting sound coming in and attaching it to meaning. And so the ventral stream, being in the left and the right hemisphere, has a strong relationship with the semantic network, which is how we understand the meaning of things. And it likely also contains the phonological network, which is our sound dictionary, the sounds of words and how they're organized in our head. So again, we think the ventral stream is bilateral and the dorsal stream is largely in the dominant hemisphere. So what you'll notice here is that Broca's area, as defined on the prior slide, is a part of the dorsal stream. Wernicke's area, interestingly enough, if you're really thinking about the dual stream model as being the most correct at this time, Wernicke's area is actually a part of both the ventral and the dorsal stream in the left hemisphere. I think that's pretty interesting because we already knew Wernicke's area was very large. It wasn't a single structure. It's very widespread, the damage that he found. And what we know today is that Wernicke's area really is made up of many different structural parts, meaning the brain structures themselves, and also functional uses, meaning that it likely contributes to both the ventral understanding route and the dorsal production route. So just as an example of how something called an area, Wernicke's area, is not truly a module in itself. You can also notice that both of these diagrams emphasize a lot of arrows. That means that we think these brain areas have to work together to do language. It's not a single area being responsible for a single part of the language system. It's really an interaction between the two, and we're learning more through MRI techniques, EEG techniques, other techniques of mapping the brain, how these areas are working together. And I'll describe that a little bit today and also in the last lecture on this series, which is more about how we recover from aphasia, what happens in our brain. I want to give some case studies because it is never a clear-cut distinction of one brain area being injured after something like a stroke or a traumatic brain injury. So the individuals that we see with aphasia have typically vast parts of their brain affected by, let's say, stroke. I'm going to show you 2 stroke examples. And because of that, because of the unique profile of damage that they have, they demonstrate very different language impairments. So this is an individual that we scanned as part of an ongoing study. You can see over to the right, I'm just going to get my pen out, or my pointer rather. Over to the right, this bottom section over here, this is a sagittal view of the brain. It's called a rendering, meaning it looks more brain-like, 3D. And you can see the darkness is the area of the brain that's been impacted by a stroke. Now, these other views are other ways of visualizing the brain, but in 2D space. So up here, you've got a sagittal slice. I know it looks right hemisphere, but it's just the way this program produces it. It's actually in the left hemisphere. The darkness, again, area affected by the stroke. This is the same person. This is just different slices of their head to show you the extent of the damage. This is a coronal slice. To remind you, it's a slice going this way, meaning crown. And you can see the darkness here is another way of looking at the same damage. Finally, this is an axial or transverse slice. This is the top of their head, A meaning anterior, L meaning left side over here. You can see the left side of their brain has had the stroke. I like these axial or transverse slices, which again goes this way in the head. You're looking down onto a brain, because it shows how deep the damage goes. So this is the outside of our head. This is what we call the neocortex. This is the cortex where a lot of our neuron bodies live. As we go toward the middle of the head, we get a lot more white matter connections, which are the axons that connect the neuron bodies together so they can talk. When we get close to the very, very center, we do have neuron bodies again. Those are gray matter, make up gray matter. These are subcortical structures here that are gray. But the important thing I want to note here is that you've got cortex damage and you've got white matter damage, meaning that this stroke has affected this person's gray matter and this person's white matter. I also wrote up here at the top, if you're interested, exactly what areas of the brain seem to be affected by this lesion. We call stroke damage lesions, by the way. Some biographical information about this person. They were 45 when they had the stroke. They identified as male, and the scans that we have here were taken at the chronic stage, meaning 40 months after they had a stroke. This is important because scans taken earlier on don't show the full extent of damage because the brain is still very, very inflamed. It's still working on dealing with the damage in its own way. It's really hard to get an idea of exactly what brain areas will end up as being non-functional later. So this is a chronic scan, meaning that this lesion is likely representative of the damaged brain in its entirety. So let's talk about what we can interpret about this person's aphasia from what we see on this scan. This person, when we did some neuropsych testing, tested as having moderate anomic aphasia. I talked about in the prior lecture, in lecture 2, how those labels can be useful, but generally they don't tell you much more than generalized ideas of what the person has going on. So what I've done here is give you some specific symptoms about what this individual was demonstrating during this testing. He was having real issues with naming and word finding. So if you gave him some pictures of things to name, even common objects, like you gave him a picture of a dog, he might produce the wrong word, but it might be a related word like cat. He would also produce sound errors, which we call phonological errors. So again, if you gave him a picture of a cat, he may have said clat. He inserted the wrong L sound into what he was producing. Now, this wasn't only when he was asked to name objects or pictures, it was also while he was just spontaneously speaking. He would often have issues finding the words he wanted to say when he was speaking. He would often talk around them. We call it circumlocution. Let's say he wanted to say the word dog. He's like, this morning I was having some issues letting out my pet. I've had this pet for a while, dog. So he was describing it before he landed on the word. We call that circumlocution. By the way, they don't always land on the word, but in that example, I was saying that he did eventually find the word dog. He did have auditory comprehension intactness, meaning that he could understand speech very well, even complex sentences. And when we tested his reading and writing, both of those were largely intact. Now, he did have some motor damage to his right hand. So when you have a left hemisphere stroke that affects a certain part of your motor cortex, it can affect the right side of your body because of how the motor system crosses over. In this case, he did have some right-sided weakness in his hand, so his writing was hard, but the language used while writing was correct, meaning that he could spell things correctly. It was just the motor component was a little sloppy for him. So over here in his brain image, we can think back to the dual stream model to try and understand how some of these symptoms are happening. You might think to yourself, these first two symptoms, and in particular, this comprehension symptom, a good thing about comprehension, he really has good comprehension, speak to us of dorsal stream damage, meaning that the majority of this individual's difficulties are in production. Almost all of his stroke here is involving the dorsal stream. So that would be a correct assumption. So we're thinking of a correct mapping of largely production errors to largely dorsal stream damage. This area right here, if you think back to the Hickok and Popel model on the left-hand side of that last slide, this is largely phonological access. So this might be why this individual is making those errors like clat for cat, just as an example. So this is a nice example of how we might be able to understand some possible symptoms from the profile of brain damage. But interestingly enough, it's not that straightforward. And I'll show you some examples of this and some reasons why it's just not possible to look at a brain and say, this person's going to present with these language difficulties. The other thing I want to note on here is that there is pretty considerable brain damage, so it's a decent amount of the left hemisphere is affected. Remember, the middle cerebral artery is the area serving this, so he probably had a stroke in that area. But he was pretty young when he had a stroke. He was 45. There are neuroplastic processes that can be completed to help the brain function better after a stroke, and those are easier for the brain to do when the brain is younger. And so what we may have found in an individual who was 80 and had this type of stroke to this exact area, let's say this exact size, we may have found very different language symptoms and severities just because the brain was unable to really restructure itself in a similar fashion. So that's something to keep in mind, as the age of stroke is definitely something that matters here. I wanted to give you one more case study that's different. So again, looking down at our rendered brain, you can see that this is a very different profile of damage. It's very, very frontal lobe. It's actually exclusively frontal lobe, and it is exclusively in the dorsal stream of language. You can see a better view sagittal here. Again, this is left. I know it looks right, but it's left hemisphere. Coronal view here, and then you've got a axial or transverse view here. This person was a little older when they had their stroke, 56 years old, identified as female, and the scans were taken again in the chronic stage, so 23 months after her event. She had a very different language profile than the gentleman that we just described. This person, when tested on our aphasia battery that we were using, tested as having severe Broca's type aphasia. Broca's aphasia does not necessarily map to damage to Broca's area. I'll show you that in a second. Broca's aphasia typically associates with real issues in producing language. So not surprisingly, this woman had severe issues with naming pictures and actions. She sometimes produced semantic errors like dog for cat, phonemic errors like clat for cat, and sometimes just couldn't produce a word at all. She was like, I don't know what that is. During spontaneous speech, similar issues, sometimes could talk around it, but many times didn't have the vocabulary to even circumlocute. Very effortful sounding when she produced language. We sometimes call this telegraphic, meaning that it was largely nouns and content words when she was speaking. They're very little by way of grammar. We call this agrammatism. So when she spoke, it tended to be things like listing, like, oh, dog, bark, sounds effortful, lacking some grammar. Now, she did have some issues in understanding speech. She had issues understanding even single words, like if I were to have said point to the picture of dog. She may have had issues even with that and extending up to sentences and understanding more complex language. And she had impairments in reading and in writing, not just due to motor, right, but due to language issues in understanding words and letter to sound relationships and writing out things that we said to her. So overall, much more severe in terms of the impairments that we saw in language. Similar in terms of lesion size, though, to that other gentleman, but very different location. Perhaps being a little bit older may have had an influence on this individual's severity, but it's hard to say. But it just seems like this individual has a very different profile of language. We can assume the dorsal stream is heavily involved due to her issues being very heavily production impairments, but she does also have some impairments in understanding language. So we might have assumed perhaps a bit more ventral stream involvement, but we really don't see that in this individual. So there's not a clear-cut brain to behavior relationship in a lot of these things that we're going to talk about. This study by Yorganov et al. In 2015 really gets at that idea of within each aphasia type, there's really not one pattern or extent of brain damage that we see. They use some sophisticated statistical modeling techniques to look at this, and what you're seeing in this image is a bunch of individuals with anomic type of aphasia, Broca's, conduction, global, Wernicke's, and we're overlapping the brain damage of all of the individuals. For example, let's look up here in an anomic aphasia. We're overlapping the left hemisphere brain damage of all those individuals, trying to see if there's a very commonly shared pattern there. The more red or the more hot colors that you see, the more often damage to that area of the brain was seen in that type of aphasia. So in the anomic group, you're seeing very little overlap, meaning that it's really unclear mapping what we see as symptoms of those individuals with the brain damage patterns that we see. Now, some are a little bit more clear in terms of brain to behavior relationships, in particular this global aphasia group, which is, if you recall back to when we talked about aphasia types in the last lecture series, or last lecture, I should say, global aphasia is the most severe. They have impairments, very severe impairments in both production and comprehension. And you can see some dark red here, and this is areas of the brain that are both in the dorsal and the ventral root of the left hemisphere. But the major takeaway is that there's a lot of shared damage across these groups. So the brain behavior relationship is just not that clear cut. When we do these types of lesion studies, we call it lesion symptom mapping, where we overlap brain lesions and we associate it with patterns of behavior. We can make some really sophisticated inferences, but they're limited. So I just want to address that here. An example of an inference is there at the top. Damage to a brain area plus an impairment might mean that brain area is necessary for the thing that makes that function possible. Example, damage to Broca's area. The people we're measuring may have a speech impairment like a language production problem or agrammatism. You could infer Broca's area is important for that impairment, agrammatism or speech, whatever you're calculating here. The considerations, though, are a little bit different. We have to keep in mind that that inference is not completely correct, in that if a language impairment can be caused by damage to a single area or a relationship of areas, let's say a network of areas, lesion-based analyses alone might miss that critical interaction between areas. So that's something that we can look at using other techniques. So we think about lesion analysis complementing these other techniques that we're using, and I'll talk about some of these now. So just to summarize where we are at the moment, we understand that there are parts of the brain that work together and are probably specialized for language. Now, I'm not saying all they do is language. I think we're still not, as a cognitive neuroscience field of language, I don't think we're there yet of saying they only do language, but they're certainly specialized for language. These parts and streams are individually specific. Over here to the right, you can see some examples of individuals doing the exact same language task in a scanner, but having slightly different profiles of brain activation when they're doing that. So they have slightly unique language centers, if we want to call it that. And now these regions lie close to regions that do completely other things that we think do other things. So language regions might lie literally right next door to regions that do multiple other cognitive functions. And that you can see over here to the right. Here's the schematic at the bottom of a language network. This is a kind of a group map from a bunch of different people. So it's a generalization of where language generally is found in the left hemisphere. And then multiple demand network, which is from this group of researchers saying that these brain networks do a bunch of other things, right? They're involved in a lot of other cognitive tasks. And you can see the language and multiple demand networks sometimes overlap and typically lie adjacent to one another. So a big takeaway right now is we think there are streams of brain areas or networks of brain areas that work together to do language, and they're specialized to do this, but they also lie very close to brain areas that do other things. So it's not just that straightforward of what Broca and Wernicke once said of this brain area does this thing, when it's gone, that function goes away. It's just not the case in that simple format. Now, I said I'd tell you evidence of how that's just not the case. So here are two papers that really get at that specific to Broca's area. In one, they just don't find that damage to Broca's area of the brain contributes to whether or not someone redevelops language production skills over time after a stroke. If Broca were right and that area of the brain were completely critical for language production, we just wouldn't find that result. Now, the other paper at the top talks more about how it's the connections to and from Broca's area that probably are just as important, if not more important, for describing our language production skills. So that goes back to this idea of brain areas working together and talking to one another to complete complex skills like language production. So to conclude, these summary images exist. I know that they're used all of the time in teaching about aphasia, and I think they're great schematics to get us to think generally about how brain maps to behavior. But I do want to caution that it's not just that clear cut. We know that it's not this simple. We know that a lot of factors come into play, like neuroplasticity, age of damage, pre-morbid language organization, meaning that every brain is individually organized. We're all a little unique as to what parts of our brain are specialized for language. So of course that's going to matter when all of us, let's say if all of us were to have a stroke, we would have different profiles of damage mapping to different language impairments because before the stroke, we had slightly different organization of language in our brains. So these images are great to help us globally think about what might be going on with brain to behavior relationships in aphasia, but it's just not that simple. And I hope that you will be excited to learn about the more complex relationships of what's going on in the brain. So these are my conclusions for now. This is a great stay tuned because this is an area that's constantly changing, which I find really exciting to be a part of. There are absolutely brain areas we know consistently become active during language tasks. Some people call them specialized areas, depends on your terminology. We think that it's not just one area does one thing. It's just too simple. We think that brain areas interact to help us do these complex human things like language. And we're constantly learning about how they do that and how damage affects those networks and the ability of brain areas to work together. If you have any questions about this lecture or in general the series, please feel free to email me below. We also are doing research involving neuroimaging. We usually use MRI. We've done functional MRI. We've done diffusion tensor imaging. Just really depends on what we're currently investigating, what question we're answering. But you can find all of our current research on the website listed here, neuralresearchlab.com. Thanks for tuning in.